Today's video is about the VSEPR theory, which stands for valence shell electron pair repulsion. This occurs in covalent compounds. As they bond and share electrons with one another, they take on these different geometric shapes: AB2, AB3, AB4, AB5, and then AB6. Along with those geometric shapes are the derivatives. So those are your root shapes. AB2, 3, 4, 5, and 6 are all your root shapes. We call that your electron geometry. And then we're also going to do the derivatives of those shapes. So your derivatives are really within the AB3 as well as AB4. And notice in your derivatives, you've got E. E is your lone pair. Your B and your E added together, 2 plus 1, will give you your 3, which is your root shape, AB3. So you have AB2E for AB3. And in AB4, you'll see AB3E as well as AB2E2. And in those different shapes and geometric, shapes, it is rooted from the AB4. Notice 3 plus 1 gives you 4. Notice 2 plus 2 gives you 4. So the root shape is AB4. We will not be responsible for AB5 derivatives nor AB6 derivatives, but we should know AB5 and AB6. So let's go ahead and create each of those shapes and their derivatives. Get your kit ready and make sure you're turning to your molecular geometry page reference sheets, which are your yellow pages. So let's go ahead and start with your AB2. AB2 is just 2 bonded atoms around your central atom. The shape and geometry is called linear. Notice the angle. The angle is 180 degrees, so 180 between the bonds. So that's the bond angle. Now we go to AB3. AB3 is reorienting the bonds such that 3 are along the same plane, and we have what is a geometric shape called Trigonal Planar. Notice when I move it this way, you'll notice that all the bonds are on a single plane. Okay? The angle for a Trigonal Planar is 120 degrees. So notice 120 plus 120 plus 120 gives you 360. So it makes a full circle. Now we will move on to AB4. In AB4, I'm going to move all of the 3 bonds in AB3 downward to make the legs of my alien. And I'm only going to move it slightly downward. And then I'm going to put the head of the alien top. Now you can think of it also as a tripod. So the way to check to see if this is all working is you put it on a flat surface and you rotate your shape around, and if the head isn't quite standing up straight, you rebond the head. So you keep on rotating around, and if you see the head is in some way or another tilted sideways, you rebond to make it stand straight up and alive. So then you've got a perfect tetrahedron. Once that happens, now you will your angles are 109.5 degrees apart from each other. So it's all equal distance in terms of the bond angles. So now we're going to move to the derivatives. The derivatives is just a matter of adding lone pairs. And lone pairs take more space, so my lone pairs are going to be these marshmallows. So I'm going to do AB3E1, basically. Now if you look at the shape, this lone pair is going to cause these bond angles, which is 109.5, to squeeze 2.5 degrees downward because it takes up more space. And this now is going to make the angle, instead of 109.5, 2.5 minus that is 107 degrees. So these bond angles down here are all 107 degrees. Now, what geometric shape do you see from this? You see actually a trigonal pyramidal. So if you look at closely, you can actually connect the ends of these bonds and you'll see a triangle coming out of that. And of course it plops up to make what is called a pyramid. So from this angle, you can see the pyramid. Now we move on to AB2E2. In AB2E2, we're seeing that there are two lone pairs and two bonded atoms here. So the shape and geometric shape that comes out of this is called bent. Notice it doesn't look like a straight line. It actually has been bent downward from these two lone pairs that are up here. So the angle here, because the root shape is a tetrahedral with 109.5 degrees, and there are two lone pairs, each causing a 2.5 degree squeeze on this angle right here, this angle between the bonds. The bond angle now is 104.5 degrees. So it's a 5 degree squeeze total. 5 degrees subtracted from 109.5 is 104.5 degrees. Now we move on to AB5. So I'll remove everything. For AB5, I like to start off with AB3 first. So I'm going to make my trigonal planar shape, my original trigonal planar shape. And notice again, all three bonds on a flat plane. Now if they aren't, you want to fix that. And notice all the angles are 120 degrees as far apart from each other as possible. Now, for us to have 5, we have to figure out where we put the next two bonds. And if you look at the area and region where there's space above the plane, the trigonal planar plane. And then there's also space below. So we're going to put the stick, or our two last bonds, above the plane, perpendicular to the plane, and then below, also perpendicular to the plane. So now we have what is called a Trigonal Bi-Pyramidal. And there's two pyramids, one on top, and then there's also a pyramid on the bottom. The two angles in this shape and geometry is, in fact, 120, where the trigonal planar shape is, but it's also 90, so it's where the top and bottom bonds, the vertical bond, is actually perpendicular to that plane. So it's 90 right here. You can see it's perpendicular. Straighten out the bonds if it isn't. So now we go on to, once again, this is called Trigonal Bi-Pyramidal with two angles, 120 and 90. Now we go to AB6. In AB6, instead of a square planar, a trigonal planar, I'm going to make a square planar in the center right here. And you'll notice when I make that square planar that if you connect all of the ends here, it makes a square. And then I'm going to figure out, where do I have space for my last two bonds? I notice that there's space on top of that square planar and on the bottom of that square planar. So I stick my last two bonds on top and on the bottom. And as a result, I have what is called an octahedral. You should see 8 faces to the shape. You have to count your faces around, but all the angles in an octahedral shape is 90, 90, 90. And whether I tilt it one way or another, again, you might need to adjust some bonds to straighten it out. Well, you will see the same octahedral shape. It doesn't change the geometry. And again, you're spacing all of those electron pairs as far apart from each other as possible at 90 degrees. Octahedral means 8 faces, so count your 8 faces all around the structure. And that ends our video. Be sure to construct all of these shapes. Bye-bye.